Hello, everyone. Yeah, so this is a this is a group effort and of an ongoing work on Mare Crisium. And yeah, so sorry. Well, okay, this will have to do. So Mare Crisium is emplaced in the Crisium Basin. So yeah, the colors are really washed out on the screen, but there was supposed to be a green circle encircling the Crisium Basin, which is a nectarian impact basin of approximately 550 kilometers in diameter. And it's filled with Mare lava, which we call Mare Crisium. One interesting fact about Mare Crisium is that there was a mission that landed there, Luna 24, in 1976, and it brought back 170 grams of soils from the surface. Yeah, and so an analysis of those soils showed that, well, the pointer doesn't work, I guess. Well, so the graph on the left shows, so those S signs on the bottom of the graph show the emplacement of the Luna 24 soil samples. So this graph represents the weight percent of titanium TiO2 against the weight percent of MgO. And so those are very low titanium basalts, pretty similar to Apollo 17 samples, which are represented by the X symbols on the same graph. And so when we look at the soil visible and infrared signature, we actually see, so here on the graph on the right, the spectra on the upper part of the graph are both from the Luna 24 samples. And we can see that the spectral contrast is actually a little bit stronger than in the spectra from Apollo 11 and 12. So Head and collaborators, after a campaign of telescopic measurements, established mapping of the Mare Crisium. And so they grouped out Mare units. So there's 3 main Mare units, and they actually relate to different TiO2 compositions. And so group 1 would have 3 to 5% TiO2, group 2 would have 1.5 to 2.5% TiO2, and group 3, 2 to 3% TiO2. And so more recently, there have been more efforts to create another updated Crisium geological map. And so it's shown here on the left. And so we can kind of see the same units. So if I can flip back and forth, you can see that the units divisions are kind of preserved, which is great. And Hiesinger and collaborator actually counted craters on those units and, well, on the units on this map from Head and collaborators, and found that the Mare units span ages from Eratosthenian ages to Imbrian ages. And they found a good agreement between the ages from crater counts in the unit on which Luna 24 landed, and radiometric ages. So that's still really good. And so for this mapping effort, we kind of threw a lot of data sets, as you can see. This is a little bit of a death by PowerPoint. So we kind of looked at a bunch of remote sensing global maps or just data, and to come up with our own version of the geological map. And so it goes from the Luna WAC global map to the DEM from the merged Lola and Kaguya DEM, Clementine, iron and titanium maps, Kaguya TC, M-Cube, so mineralogy mapper data, diviner rock abundance, mini RF data, and Grail crystal thickness maps. And this is very bad because the colors are washed out, but this is our version of the geological map. So you can see again that the same units are kind of represented. And so it's great. We agree. Yay. So we did this mapping based on iron and titanium variations with the Clementine data. And the little, well, actually the really big triangle here. Oh, here's the pointer, great. So this represents the location of the Mons Trail, which is a volcanic cone on one of the Mare units. We also did some crater counts, and the Mare units are consistent with Imbrian ages. And then we went ahead and characterized the signature of those Mare units using the M-cubed data. And so I'm going to show you spectra from the pink, purple, yellow, and orange Mare units. Okay, it's going to be really hard to see here. But okay, so if we look at this Selene evening map, we can see here Mons Trail, which is a volcanic cone. And actually we see two other little cones here. And in this Clementine color composite, they actually pop up as red, which would be significant of low titanium or high glass proportion. And if we look at the M-cubed band centers, this graph represents the band 1 versus band 2 centers. And so here we have the Mare units in blue, and they are kind of all grouped together. Here in yellow, this is Mons Trail, so the volcanic cone. And then just for reference, here in red, this is an LCP, so low calcium pyroxene from Relab. Here is the high calcium pyroxene from Relab, and here green glass from Relab, and here an orange glass from Relab. And so which is interesting is that Mons Trail has kind of a similar band 1 center to the green glass. And then the band 2 is kind of in between the high calcium pyroxene and then the green glass. Okay. So the reason why we kind of wanted to go back to Mare Crisium is that there is a growing interest on it, because the Blue Ghost Mission 1 aims at landing in Mare Crisium. I put 2024 plus because the launch should be in November of this year, but yeah, I'm not sure of the path that they will take, so I'm not sure when it will arrive. And yeah, some landing site constraints have been published by Nagihara and collaborators, and they kind of made a list of different constraints to use in order to produce a landing site that would be good for Firefly to go to. And three of those constraints are payload related. So the crust should have a uniform lateral thickness. There should be no strong magnetic anomalies, and then the eastern side of Mare Crisium is preferred. Okay. Oh, and yeah, this is Firefly. And here the list of the payloads that are already selected. So Nagihara actually proposed to go there. So it's close to Mons Trail. It's kind of to the north of Mons Trail. And they they provided this landing ellipse based on the calculation on LOLA DEMs. And we used we proposed alternative landing sites meeting the engineering and payload requirements to kind of maximize the geological diversity, or like to maximize the science that we could get from it. And so here in red, those are the magnetic anomalies to big no-nos. And all those green stars are proposed landing ellipses. And here, this table actually presents a bunch of, well, those are just the sites. So here again, the location of the sites. And so we have several parameters like the mini-RF CPR, the Kaguya mean slope, and what we see here is that the Blue Ghost original site has actually a higher slope than the other ones that we proposed. And those are actually two close-ups of sites that we propose. And so we actually propose one of the sites to go south of Mons-le-Trail because it would be nice to kind of see in the inside of this hollowed out cone. I mean, I think it would be exciting. Then another site would be to go here. So it's kind of close to another cone and also close to a wrinkle ridge. And then another site would go close to a buried crater rim and a wrinkle ridge. I think I really flew through this presentation. So, okay, great. So yeah, in summary, we agree with the mapping efforts that have been done before, which is great. Always good to agree with previous works. And we have Mare units that span between 3.6 to 3.2 billion years and numerous wrinkle ridges. We have, the M-cubed spectra show a very uniformity of Mare units, but we do have some variations in iron and titanium abundances as seen by Clementine data and also in OMAT maps. The rays of Proclus crater, which I actually didn't show you, but okay, so there is rays a little bit all over the surface coming from Proclus crater, and they would actually provide rocks from non-Mare material, which would be also very exciting science-wise to analyze. And then we found two additional volcanic cones that would be really interesting to go and just visit. And yeah, they are 2 and 3 kilometers across, so it's a nice size. And yeah, that's it. I'll leave you with this. Thank you for your attention.
Any questions for Mélissa? Well, I have one. Yeah, I was interested to see those cones, and they look like they are associated to some structural features. They are basically in correspondence to either wrinkle ridges or some crater rims. I was wondering how many you see in total in your map, and if you see some sort of relation between these two things, the structures and the cones.
Yeah, so we see 3 volcanic cones, and we would have to check for, but there is definitely some wrinkle ridges close to them. So yeah, there must be some control. Yeah.
Any other question? Okay, I may have one more question. Did you also how to say, went more in detail on the type of volcanic classes you expect outside those cones, if you know anything about volatiles content you can expect, or if you plan to do that?
Yeah, I would love to have the answers, but it's an ongoing work, so I don't really have a lot of details. Just yeah.